Hi.
Welcome back to the IB Physics series, and today I'll be looking at thermal energy transfers, which is topic B.1. So let's get into it. So the first thing you need to know is the states of matter. So in IB Physics, there are three states of matter, and you probably already know these: solid, liquid, and gas. Those are the most common states of matter, and there's much less common ones like liquid crystals, plasma, and some really interesting ones here, like a fermionic condensate, a Bose-Einstein condensate, supersolids, neutron degenerate matter, which we look into in topic E. But like these are not in the IB physics syllabus, but if you go on to study theoretical physics later, you'll probably encounter them. So yeah, for IB, you just need to know solid, liquid, and gas. So solid is basically when particles are closely packed and they can't move. This just means that they vibrate in very, very small radii or in very small motions, and they have very low energy, right? And yeah, that's pretty much it. And solids have constant shape, they have constant volume, and they're highly dense. So for this sort of topic, there's just a lot of memorization. It's not really that difficult. Then liquid is basically when particles are tightly packed, but not so tightly packed as compared to solid, so it's just medium. And then they're randomly arranged and free to move compared to solids, and they have medium energy as well. Liquids also have constant volume, but they don't have a constant shape, unlike solids, because solids they're fixed in the shape, but liquids, they take the shape of the container they're in. Like if you pour water into a glass, then it has a different shape, right? And then gas is basically when the particles are far apart. They're randomly arranged and they move at very high energy, so they move very quickly and they are very, very small. This means that they don't have a constant shape or a constant volume. So some examples of gases are air, helium, ozone, CO2, and water vapor. We'll have to look a bit more in depth on these in B2, but for now you just need to know that gases have non-constant shape, non-constant volume, and you need to know the particle properties. So now let's look at densities. So density is mass over volume, and density is this little p here. It's called rho, it's a Greek letter. And m is mass and v is volume. So it's just a measure of how tightly something's packed. And that's pretty much all we need to know about density. You actually probably remember density from Unit A when we found this in order to calculate buoyancy. So now let's look at Kelvin. So this is basically a way to measure temperature. It's the standard unit for temperature, and it's the unit that we always use in calculations in IB physics. We never use Celsius, only Kelvin. And it was invented by this guy, Lord Kelvin. And it's basically just found by adding 273 to the temperature in Celsius. So usually they'll give you the temperature in Celsius to trick you. All you need to do is add 273 to that. So now we look at kinetic energy. This is basically going back again to topic A, where we recall that energy is a half mv squared. Now we know that for a particle, so like for something in a gas or a liquid or a solid, usually a gas because this is an ideal gas law, is what we know to call it later. This is equal to 3 over 2 times the Boltzmann constant times temperature. So Kb is the Boltzmann constant, which is roughly 1.38 times 10 to the 23, negative 23, and it's measured in joules per Kelvin. And then temperature is measured in Kelvin, and this is just measured in joules, because joules per Kelvin times Kelvin is joules. So this is now internal energy. Internal energy is kinetic energy plus potential energy, and it's represented by this little u here. And potential energy is basically based on the space between molecules. So solids have very little space between molecules, as you can see here, but gases have pretty high space, and this has medium space, as you can see. So for a solid, it has the lowest potential energy, and the gas has the highest. And basically, internal energy, as you can see here, just increases when EK increases or when EP increases. So when there's a change of state, so a solid becomes a liquid, or when the temperature of the solid increases, because as we can see here, EK is proportional to temperature. So next we need to look at equilibrium. That just means that when two substances reach the same temperature, there is no energy transfer because energy always goes from a hot object to a cold object. So when they're the same temperature, neither of them is hot relative to the other, and neither of them is cold relative to the other. So it just kind of stops, as you can see on this graph here. It equals at some point, and then it just stops transferring. Next, we need to look at changes of state. So thermal energy is transferred, but there is no change in temperature. And this is when the state changes. So for example, when water freezes, water will be at 0 degrees Celsius, and between that point in time and that it forming ice, there will be no change in temperature, but there will be thermal energy kind of flowing out. And there's 4 methods to cause a state change. Those 4 are melting, freezing, vaporizing, and condensing. So like right here, you can see an ice cube and it's releasing water, so it's melting. You probably know these 2 words quite easily. Vaporizing just means that vaporizing and condensing are just to do with gases. So like this is basically forming water vapor, and this is the exact opposite, so going from water vapor to water. Next, let's look at specific heat capacity. So this is a formula you need to know. Q equals mc delta T, where Q is thermal energy, m is mass, C is specific heat capacity, and T is temperature. So delta T is change in temperature. Now note, delta T can be in Celsius or Kelvin. It does not matter because you're just adding 273. So you do plus 273 plus 273 and then subtract. So the difference is actually the same. So it doesn't really matter what unit delta T is, but temperature on its own is always Kelvin. Mass is in kilograms and this is in joules, which means that C is just joules per kilogram per Kelvin. So that's the unit of specific heat capacity, joules per kilogram per Kelvin. Now this is quite important. The specific heat capacity has a very specific definition and you need to know it. And that definition is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 Kelvin. And that's pretty much it. So now let's look at specific latent heat. That says Q equals ml. One thing to note is that you can't just equate these two and say that C delta T equals L. That's because they apply to different scenarios. This one here applies to when there's a change in temperature. This one here applies to when there's no change in temperature. And we'll look at that on the next slide. But here, all you need to know is that Q is thermal energy, M is mass, and L is specific latent heat. Because Q is in joules and M is in kilograms, L has a unit, joules per kilogram. And it's basically the energy required to change the state of 1 kilogram of something without changing the temperature at all. There's 2 types of specific latent heat, latent heat of fusion and latent heat of vaporization. They're just written as like L with a small f or L with a small v underneath. Fusion just means it's for solid and liquid. Vaporization just means it's for liquid and gas. So for a solid becoming a liquid, it's F. For a liquid becoming a solid, it's F. For liquid to gas, it's V. And gas to liquid is V. That'll be given in the question usually. And let's look at what I was talking about earlier. So I was saying that mc delta T is for a change in temperature. So as you can see on the vertical axis, here there's a change in temperature. Here there is no change in temperature. So here we use mc delta T, here we use mc delta T, here we use mc delta T, and here we use ml, and here we use ml. because there's no change in temperature. It stays constant throughout. Um, so now let's look at conduction, convection, and radiation. They're all methods of energy transfer, and the most common is called conduction. It's the way how two solids transfer heat, and it just means that heat goes from hot to cold when they touch. So when two objects touch, it becomes hot to cold, cold to hot. So yeah, that's basically all we have to do. And metals usually conduct well, but wood doesn't, right? So um, metals are good conductors of heat, and wood is a bad conductor of heat. So that's basically what conduction is. And it's basically modeled by this equation right here. Delta Q by delta T is Ka delta T by delta X. So all that means is that the rate of change of thermal energy with time is equal to a constant K that's always given in the question, and it's specific to the material. So for instance, rubber would have a different K to wood. A, so that's the cross-sectional area. Usually it's for a square, but sometimes a circle. Delta T is the change in temperature, so the difference in temperature between the two ends of the rod. And delta X is the width of the rod, and that's also given in the question. Next, we look at the other method, convection. Now, for convection, you don't really need to know any math. You just need to know that hot air rises and cold air falls. So warm molecules move up, cold molecules move down. This also works for waters, but it's less common for fluids than it is for gases. But it most definitely happens, like, for example, when you're boiling water, that's convection. And it happens because of differences in density. So hot air is less dense than cold air. So cold air falls because it has more mass per volume than hot air, and hot air has less, so it rises. Now let's look at radiation. So this just means transfer by electromagnetic waves. We'll look more into that in topic 3, C. But right now, all you need to know is that it just means that you are transferring through electromagnetic waves. And it's sort of modeled by this equation. Lambda max times T is 2.9 times 10 to the negative 3. That looks like a random number, but it's called Wien's law. And he basically found that if we simplify this, it roughly equals 2.9 times 10 to the negative 3, where lambda max is the maximum wavelength and temperature is T. So at any given point, lambda max and T are basically equal, and we'll always use this point here because we're using maximum wavelength and not this one here, right? So that's pretty much it. And so lambda max is the maximum wavelength. That's all you need to know for now. In the future, you can understand that we have some more definitions and we go deeper into this. But for now, this is all you need to know. And T is the temperature in Kelvin. Basically, all we need to know is that wavelength and temperature are inversely proportional, and that the graph of intensity to wavelength looks something like this, and it shifts right as the temperature decreases. So one of the last concepts is apparent brightness and luminosity. Apparent brightness is how bright something looks on Earth, meaning how much power it receives on Earth. And luminosity is how bright something actually is, so how much power is emitted by a star. And B is basically apparent brightness, L is luminosity, and they're related by B equals L by 4 pi d squared. So this is basically the shadow that Earth casts, as kinda is a way you can think about it. So if you think about Earth, it sort of casts a shadow. It has a surface area basically at any given point of 4 pi d squared from the top. So that's like a bit weird to think about, but that's true. And the last thing you need to know here is that power is equal to sigma times area times t to the 4. And yeah, sigma is a bit of a funny name to have, but that's what the symbol's called. And the sigma stands for 5.67 times 10 to the negative 11, which is Stefan Boltzmann's constant. And A here is the surface area, and usually we talk about this for planets, so it's 4 pi r squared because planets are can be assumed to have a spherical cross-sectional surface area at one point when you're looking at it from any direction, and then T is the temperature in Kelvin. So that's pretty much all we need to know for B.1. Now I think we can do a practice question, so I'll pull that up really quick. Have a go at this question. It says the electromagnetic spectrum radiated by a black body at temperature T shows peak wavelength lambda p. What is the variation of lambda p with T? So we're looking at how the maximum wavelength varies with temperature. Now, looking at this, you might be tempted to say, oh, it's option D because this looks exactly like this. But you'd be wrong, because this, if you look carefully, is wavelength and radiation intensity. But we're not looking for intensity here, we're looking for temperature. So D is just meant to throw you off. It's either A, B, or C. Now, when we look at it like this, if we rearrange this for temperature, which is on the y-axis here, for lambda max, which is on the y-axis here, we get lambda max is 2.9 times 10 to the negative 3 divided by T. If we graph something of that sort, we usually would get a reciprocal function, something that looks like this, something that looks like 1 by x in math, as you would say. So it actually goes like this. It can't be a straight line because we have something divided by a variable. So it's actually option A here because it curves down and it changes. It's a reciprocal graph. So the correct answer is option A. I hope you found this video helpful and thank you so much for watching.